Hey guys, welcome back. This week is election week, so if you can, go out and vote tomorrow. And if you want, try to convince your friends to vote. I think I don't like to be political, but it's just the one thing I'm going to say about the election. I think it's really important that we all vote, your voice be heard, even though I totally disagree with the electoral college. I think it's a ridiculous policy we have here in America. But I've been feeling really, really anxious about the election, the status of our country. So I just wanted to kind of tell you guys, if you can, go out and vote tomorrow. Or if you're doing mail-in balloting, go and drop off your ballot. Don't mail, because it most likely will not count. And um, the the whole issue was voter suppression will probably kick in at that point. So it's really too late to mail in your ballot. You must go and drop it in. But anyway, um, that's my kind of you know thing about politics and voting. So if you can, please go vote. All right, so we're going to jump right back into chapter 11. So I graded a quiz. It's online. Most people did. Most of the class did better than my last year. Some of my sections last year. So I'm pretty happy about that. If you're not happy with your score, I think you should look at the quiz. I'm going to post the key probably after this lecture is done recording, and then go over the quiz, see where you went wrong, see where you need to probably brush up studying. So for studying the quiz, if you do the active exercises, they pretty much go over the stuff I test, especially in the word solving problems. So every word solving uh, problem on the quiz on part 3, we did example of each in the active exercises. So if you didn't catch those, I would highly recommend watching them. And for the multiple choice, some questions um, may have seen out there, but I can guarantee that I went over them in detail in my lecture about gases specifically, especially gauge pressure. Um, the actual pressure is actually the absolute pressure, so you must take into account both the atmospheric and the gauge pressure to actually calculate the actual pressure in the tire. So a lot of students missed that question, and a lot of students missed the last question about perfume filling the room. So the thing about perfume, there was a lot of good acceptable answers, but the one thing you should know that a room smells because perfume is released in the air. It moves. It smells like perfume a while later because the gas particles are moving fast in straight lines um, in all directions. Right. That's why the gas permeates throughout the room. So that was the answer I was looking for. That it moves in straight lines, or you have to take in consideration the velocity. So some people got it, so that I was happy about that, but a lot of people missed it. And a lot of people, the other common question they missed was the pure substances. So remember, a pure substance is only a one element or one compound. So the answer here I was looking for was ice and gold, because gold is an element. There's no other type of gold of other there's no other foreign or other material in there. So gold is the pure element. A lot of people chose air as a pure substance, but air is actually kind of vague because air is composed mostly of nitrogen and oxygen. So those are two different elements or two different diatomic molecules. So they're actually, air is actually a mixture, not a pure substance. Okay, so for the next big exam we have coming up in around 2 weeks, after 2 weeks time, a little less than 3 weeks, is the midterm exam. I'll post a practice exam from one of my sections last year. So for the midterm, we got to like chemical nomenclature, which is I think chapter 7, which I think, or I think it's chapter 6 or 7. I can't recall off the top of my head, but I don't know if we'll get that far. This chapter is pretty long and it's pretty dense. Chapter 11, I would focus a lot of your time studying chapter 11, because some of the stuff can go over your head, especially in chemistry. We'll be talking about quantum mechanics, so a little talk about physics, but we won't talk too much about we won't go into too much detail. We'll stick to the bare basics of what you expect in general chemistry. So we talk about quantum numbers, electron configurations, and stuff like that, and we'll go slow and make sure everyone is on the right page. So I will highly recommend you read. You can read the book for more information, but I would use the book and the homework for extra practice so you guys can master this material. Okay, so last time we stopped at talking about electromagnetic radiation, and we were talking about the wavelength and the frequency. So this is the electromagnetic spectrum of all the possible electromagnetic radiation that is present in our world. So you see here at the bottom, we have our wavelength in nanometers. So wavelength is usually reported in nanometers. You could use whatever scale you want, but nanometers is usually what we ask in our questions. Frequency is on the top. You see here the much higher, shorter wavelength has a higher repeat, so a higher incidence where the wave goes up and down within a certain time frame. So that's called the frequency. And the shorter the frequency, the higher the frequency, the more energy it has. So you see here, gamma rays, which is, which is the highest form of energy we know, and that's usually associated with nuclear radiation or the fallout of nuclear processes with radioactive isotopes. So gamma ray are really bad. They are called ionizing radiation because they can perforate the body's skin, and they can cause damage to DNA, and that's what causes that's one causes of cancer. So so if you know who Marie Curie is, she's a very famous nuclear chemist. I believe the first female chemist to win the Nobel Prize. Her lab note, she studied nuclear chemistry, and people still can't access her lab notebooks because they are they're still radioactive because of her research. So radioactive stuff, they usually the half-life or for those radioactive nuclei to decay, they could take a very long time. So she was born probably roughly in somewhere in the 1900s, and still to this day they still can't access her notebooks because the fall of the radiation is still present, and you can't go there because it'd be a risk. So I mean, it's even a risk to approach them, but it's even a risk to handle them because you can't speed up these processes. But nuclear chemistry is something we won't be able to talk about. You'll talk about that in probably Chem 2C, the third quarter of general chemistry, the last quarter. But that's kind of where gamma rays comes from. X-rays, we use X-rays in instruments to visualize, bone structure. We also use it for crystallography to visualize crystal structures. So that's a very important topic for inorganic chemists and organic chemists too. If you need to deduce a structure of a new compound, and you don't have any other techniques, and X-ray gives great visual information, and you could deduce the actual structure bond by bond. So X-ray is very valuable, not only for very new crystal structures of inorganic or metal compounds or metal complexes, but also for organic compounds and the framework. Then we go ultraviolet. So UV and the visible spectrum are kind of hand in hand. There's something called UV vis spectroscopy, and things with color usually have um, a property called absorbance, where they absorb light and they give off light of a certain color back. So UV vis is both applicable to colored substances, like like the color of a carrot. There's a molecule called beta carotene, and that molecule gives off its rich orange color. And there's also compounds that are not colored that we can detect by, we can use UV vis to give information about its absorbance properties or how it interacts with light. UV is also given off by the sun. That's why you need to wear sunscreen when it's very hot out, because the ultraviolet rays can actually burn your skin. And the reason we survive in the presence of the sun is because there's layers of molecules in the air. One's called ozone that actually absorbs the UV rays and protects us. So it's absolutely essential that we stop polluting the air, because our ozone layer might be destroyed by our man-made, appliances, stuff like that. So yeah, climate change goes way back. There's a long history about what's been done, what's we tried to correct, and what's currently being debated. But anyway, next we have IR. So infrared is pretty much anything that gives off a heat signature, like a fire has infrared. You might have heard of infrared in like maybe movies or something, like infrared sensors or technology. So near infrared is kind of in the it's not it's between it's just before visible spectrum. So IR is perfectly safe. We if we're exposed to it, it's going to be as as harmful as visible light, and visible light does not harm us, right? Because we see it every day. Microwaves, microwaves is for rotational spectroscopy, but we're not going to talk much about that. Microwave, it's the stuff that the waves that are given off in your cooking microwave. So the same thing. There's also microwaves that are used for chemical reactions, but usually you don't encounter that very much. So that's one. So we could see the size relative of these waves, of the wavelengths, based on these pictures here. So X-ray is really small, size of the atom. Then as we go down to radio waves and microwaves, we can see that our frame of reference for the size increases. So as we get towards microwaves and radio waves, we see that the wavelength is the size of the thickness of a CD, or the width of a CD, and then 10-0, we have a picture of a dog. So radio waves, we see that there's a frequency for FM and AM. You might have noticed that. So there's a certain frequency range that we can hear and see. The radio waves is kind of that range that we can perceive. So radio waves is radio on the car radio, any kind of radio with antenna. Then there's long radio waves like that at the end. Radio waves is also used in phones, so like cell towers. So they're very low energy radiation. That's why we can talk on our phones for so long or interact with them. But you shouldn't stare at your phone for too long. Your eyes will probably get tired. Okay, so that is electromagnetic radiation. So let's switch gears here. So that's just a visual aspect of the types of electromagnetic radiation. So one common question I like to ask, like, which form of electromagnetic radiation is of lowest energy, or of highest energy, or of longest wavelength, or of lowest wavelength? and you just need to be able to imagine this pattern here, so you could recall that information. And I think for the midterm, I will allow people to make index cards because there's just a lot of information here that we're going to be tested on. So I'm totally open to doing that. A 3x5 index card where you can write some stuff down if you want. Okay, so let's switch gears. So we're gonna share something new. Okay. All right, so let's go back into here. So we were talking about electromagnetic radiation. So there's two types of spectra that's associated with electromagnetic radiation. One is called continuous spectrum, which is band of colors that result from electromagnetic radiation. Emission. So emission means give off. So it gives off radiation, or like it releases radiation, in case anyone doesn't know. Emission over a range of wavelengths. So what this means is that if a light source has a continuous spectrum, that means if you visualize it under a certain instrument, that you should see like a rainbow of colors, like a continuous spectrum of a rainbow. So like a rainbow of colors. Next we have line spectrum. So line spectrum, instead of seeing like a continuous band of colors, you see individual lines of specific colors, and that gives us information about the source of the light and kind of the element that maybe the source of light came from. So line spectrum, spectral lines. That appear. When light emitted from a sample. Sample is analyzed in a spectroscope. So in my other class, I had my students make a handmade spectroscope and look at it at different sources of light, sunlight, their kitchen light, fluorescent light, maybe in the hallway or the bathroom. And it either produced a continuous spectrum or a line spectrum. And they had to do a worksheet on that. So I thought that was pretty cool. You guys don't have to do that. You already have homework to worry about, but that's just something I want to bring up about the spectroscope. So you make a spectroscope using like cardboard, and then you put a piece of a CD in there, and that CD actually the shiny part of the CD. If you look at the CD, it looks like a rainbow at certain angles to light, and so what it does in a spectroscope, it acts as a diffraction grating. So it'll diffract light as it comes into the spectroscope, and depending on what kind of light source it is, it'll separate the light into either a rainbow band, a band of all the colors continuously, or lines that have specific colors and are spaced out on the viewing part of the spectroscope. So I think that was pretty cool. So yeah, that is what a spectroscope does. Yeah, we had to get creative because in lab we're not allowed to go in lab anymore. So we have to kind of be creative in how we talk about chemistry, and especially how we teach the labs now. So anyway, it's analyzed in a spectroscope. So yeah, if you're interested in making your own spectroscope, it's very easy. You can look online. There's multiple ways. The one I kind of had my students do was the one by the Royal Society of Chemistry. It's pretty simple, and you can't go wrong. But if anyone's interested, you can always take a look. Okay, so what do we mean by discrete lines? Okay, so discrete lines. Discrete lines, separate lines. Separate lines of color. To indicate that they are individually distinct. Visually distinct. Okay, so that was the kind of line separation I was talking about in the spectroscope. So those are that was what you would see. And the thing is that each element will give off a certain line spectrum. So you can use the line spectrum to kind of tell what element it is. So each element has a unique line spectrum, has a unique line spectrum. So usually in a lab setting, we would set up different gases of certain elements, and we'll have you predict, or we'll give you certain light sources that are a specific element, and you have to tell us which element it is based on their line spectrum. So what this tells us that the separate lines, that energy is released in a certain way. So energy here, energy released by electrons. Is in the form of a massless packet. So massless packet of electromagnetic radiation. Called or known as a photon of light. So these photons, they carry energy in specific amounts. So that's what we that refers back to the particle nature of light, and we call these photons quanta, and they mean that energy is released in certain amounts, a finite, certain, discrete amount, and that's why we get these line spectrums, because each line represents a specific amount of energy. So then we go back to the wave particle duality. So the dual nature of light. So we say light has both wave-like properties and particle-like properties. Particle being the sense of a photon, and wave being that it has a wavelength and a frequency associated with the radiation of light. Okay. So, all right, so there's a few pictures I want to go over. So we're going to switch back to these lecture slides. So this is chapter 11. Okay, so see here, wave properties is like the light moves like in a wave like pattern. And you see here, the distance between two crests is the wavelength. So if we use this log as our time interval, we can see that the frequency of the part box A is you have a single wavelength occurring before it hits the log. And in the bottom, we have multiple wavelengths hitting, passing before we hit the log. So we say in part A, that has a longer wavelength, lower frequency. And then box B, we have a higher frequency because the amount of crest that occurs before it hits the log is greater. It's about three wavelengths, 3 wavelengths. And we say that the wavelength is shorter, the frequency is higher. So that is the wave properties of light. Okay. Next, we can, if you shine white light through a prism, you can visualize a spectrum and separate all the colors. So that's pretty cool. And that's what the spectroscope does. So you see here, we pass the white light through a slit to isolate the beam. So one ray of light comes in. Then the prism here, it deflects it and splits the wavelength, the white light into the colors. So in this case, this is an increasing, continuous spectrum because there's no distinct lines in the spectrum. And you see here, as we go from violet or blue to red, that goes from lower, higher frequency, shorter wavelength to increasing wavelength, decreasing frequency. So red has the longest wavelength, around 650 nanometers. Violet is around 400 or 450. And anything outside those ranges are different kinds of light. So this is the separation of white light. Okay, so we can also use a gas discharge. So when you charge a gas or when you heat it up, it'll cause electrons to release energy. So for example, here say we have hydrogen gas, and we it's a gas discharge. So when we kind of give it energy, the gas will release energy in turn. So that light that's given off by the discharge of this hydrogen here, this purple color, we say we can pass it through the same slit or same aperture, and then hit a prism as a diffraction grating or diffractometer. And you see here that will split the light into distinct, discrete spectral lines there. So we can tell what colors are made of that light. So in this case, you have an assortment of colors. If you look at fluorescent lights, you can actually see a whole bunch of lines. So I think that's pretty cool. But so this is an example of a line spectrum. Okay, so here are different examples of line spectra. So here's hydrogen, see hydrogen here. Then we have mercury, and then we have neon right here. So this gives us an idea of all the kind of what makes up an atom, like the energy levels. So we'll be talking about the energy levels of the atom next. Exactly where we're going. Next, we're going to talk about the Bohr model of the atom. So let's switch gears again. So let's go back to the whiteboard. Okay, so now let's draw a line under here. We're going to talk about what do these lines mean. So let's talk about the Bohr model. Bohr model of the hydrogen atom. So we talked about the nuclear model, but now we need to talk about the Bohr model and what does it mean in terms of quantum mechanics? What does these light results mean from the spectra? So what we say is atom consists of a dense nucleus. So I want I might ask a question about the Bohr model, but it's very rare. I usually like asking about the sub of the energy diagrams, the sub levels, but we'll talk more about that when we get there. So, but I would try to digest the information slowly and make sure you understand it. Making flashcards, I think, for like stuff like this helps. I'm not totally against flashcards. Um, in fact, I used flashcards before, like to study languages like Spanish and Japanese before, so they were helpful. So I encourage, if you think flashcards is going to help you here, I would do it, because quantum mechanics can be a little bit tricky. All right, atom consists of a dense nucleus which contains all the atoms positive charge, and nearly all its mass. All of its mass. So good. So that's kind of what we predicted from the nuclear model and Rutherford's experiments. Now let's talk about the electrons. Negatively charged electrons of small mass travel in orbits around the nucleus. So you kind of can think of this as like the very, very miniature model of the solar system, where smaller bodies of mass orbit around a much larger body of mass, say the star or our star, the sun. So it's kind of the same idea here, but on a miniature scale. You know, the large mass in the center and electrons around it will orbits around the nucleus. That's kind of my analogy for kind of visualizing that. So the Bohr model also will state that most of the atom is empty space. Is empty space, and energy possessed by the electron in a hydrogen atom and the radius of its orbit are quantized. Hydrogen atom and the radius of its orbit is quantized. So what that means is that the energy between the electron and from the nucleus, that energy is a specific amount. So we say it's quantized, or there's a specific exact quantity of energy associated with it. So, and I'm going to explain those definitions. Quantized So let's talk about quantized. So we say it's the amount limited to a discrete set of values. So don't worry about what discrete set of values mean. It's just to describe an electron, and we'll talk about what that means later. But it's a specific amount. So it's just saying it's it's an amount that's specific to maybe say like one of the electrons we're talking about. So quantized means that the energy is specific, and it's limited. So there's a certain amount of energy associated with, say, the electron that we're talking about here. So amount limited to a discrete set of values. Continuous. So continuous means amount that can have any value So another way of putting this is that between two values is an infinite number of values. So this might sound really weird, but if you do the problems that are associated with this specific subject in the book, I can assure you it will explain it better. So there are examples which I cannot get to because we had to get through the rest of the lecture. But if you're confused about what that means, you can look at the exercises in the book. So basically, values can be continuous. It can have any value between two set of two boundaries. Between them, there can be any value, but in quantized, there can only be one value that is specific based on these discrete set of values. So there will only be one value amount. So so there's an amount of energy that's associated with these specific values, and that's it. Whereas continuous means it can have any values. There's an infinite number of values between these two boundary conditions. There's an infinite number of values that maybe something can be. So I know it's very abstract, but please stay with me, and I'll explain it more. We're going to get into more about what quantized, what will it look like when we talk about this definition. So we say an infinite number of other values. Okay, so let's go back to this very helpful slide here. Okay, so we can see the slide, right? So the quantum concept is like this. Say you're going up a staircase, and the steps represent different levels from the bottom to the top. So that's kind of like where how the quantum concept of the Bohr model is in the atom and the electrons. So you see here, at the bottom is the ground level, so that's the ground state of, say, like atoms, where the energy is the lowest. And as we move up a step, we get to the first excited state, or the H1, or the one level above the ground state, which is H. Then as we move up more steps, we get to the second level, third level, and then eventually we get to the top level, which is represented by H here. And that's where we as we move up steps, we're getting further away from the nucleus, right? Because at the bottom, that's where the closest the electrons are to the nucleus of the atom. We say that the orbits are in levels like 1, 2, 3. So by quantized, we say that this H1 energy level, it has energy that's quantized or associated with it. So it can only take on a set of discrete values that are specific to that energy level. So each energy level will have a set of discrete energy values, and that's represented by the electron. Because we can say, oh, what if the electron's here? Is it here? Is it here? Or is it here? And there's actually no way knowing for certain where it's at any point. You can know the probability of the electron being at a specific point in the atom, but you can't know for certain this property. And that's one of the things about quantum mechanics. So this picture, what you should take away is that electrons, they occupy different energy levels, and those energy levels are at different distances away from the nucleus or have different radii or radius values. And what they say is that the energy associated with each of these energy levels is it has a unique amount associated with it based on values that describe the electron. Okay, so let's look at a more schematic picture of this. So say it's right here. Usually the energy we associate with an electron when we associate them, they have this value right here, on the order of 10 to the negative 18 energy. So that joules is the SI unit for energy. So you see here, as we get closer to the nucleus, the energy decreases, right? You get more and more negative. So here's the ground state closer to the nucleus. So it should have the most energy or the lowest energy associated with it because it's very close to the nucleus. And if you were to calculate energy, right, you take the attractive forces between the positive charges and the negative charges and divided by r squared. That gives you the attractive force. So the closer you are to the nucleus, the higher the value and more negative it will be. So as we go further away, so this is going to the second level, third level, fourth level, we see that the energy between the nucleus and the electron in that orbit will decrease and get higher in energy. So we could call and then I'm not sure what these letters mean. Yeah, I'm not sure what these letters mean here. These three seem to be pointing to the first principal energy level, and these two are pointing to 2, and this is to the third. But the radii is very small. The atoms are on the order of negative 10 meters, so almost close to picometers. So see here, the radius here is very small between the nucleus and the first level, but as we increase here, the radius will increase further away from the nucleus, and eventually you'll get very far from the nucleus. That energy value will be very small. So the energy, so don't worry about too much about calculating energies. Just know that the energy associated is negative because you're talking about an electron, and that's the negative charge there, and that the radii is very small. So this gives you an idea like the different energy levels associated with the Bohr model of the atom right here. And we'll talk, this is a very, very crude picture of the orbitals. So we're going to talk more about what they actually look like. Okay. So yeah, I'm still not sure what these letters actually mean. I would ignore them. Yeah, I'm not too sure what these letters actually are describing, unfortunately. They may be describing oh, I see what they're describing. So they're describing like energy levels here. So the distance of the transition from 1 to 2 is represented by C. Transition from 1 to 3, right here, 1, 2, 3, that's B. 1 to 4. And here's another transition, 2 to 4, 2 to 3, and 3 to 4. So those are just different. So the arrows will tell you, they'll give you specific energy values. So so see here, C1, 2, that's a very the energy levels here, they're increasing, right? So as you go from 1 to 2, that distance is small, but from 2 to 3, it gets a little bit bigger. Then 3 to 4, you see here the distance gets bigger, even bigger. So these are talking about the different transitions of energy levels. So 1 to 2, the energy transition from 1 to 2, 2 to 3, 3 to 4, 2 to 4, 3 to 4. So those are the transitions. But I would not worry too much about that. Okay. So now let's talk about more about the Bohr model. So let's go back to the whiteboard. Okay. So those letters are going to make sense now. This took me a while to kind of refresh on what they were. Okay, so now we have, so now we're going to talk about something called quantum leap. So quantum jump. It's also called a leap. So what this is that the movement of an electron within an atom from one energy level to another. So those are the letters I was talking about, those transitions from 1 to 2 energy level to the 3 to 4, etc. To another without measurable passage through energies in between. So what that means is we can't measure the so we can't measure like halfway through level 1. We can't measure the energy it takes to reach halfway through the 1 to 2 level. Say we're jumping from the 1 to the 2 level. We can't stop midway between the two and measure that energy. We can only measure the distance between the 2 energy levels, that whole energy distance it takes to make that jump. So that is what a quantum jump is describing. Passage through energies in between. Okay. So normally electrons are found in their ground state. Unless you shine light on them or give them energy, they will not be found. They may be found in excited state. So electron is normally found in its ground state. So hopefully you guys are sticking with me. Trying to go slow here. So ground state, what is the ground state? So just think of like ground level, like on Earth, it's the lowest. Before sea level, it's the lowest, place on Earth that where we're floating on the surface. So ground state is state of an atom in which all electrons occupy the lowest possible energy levels. So the lowest possible energy level is the electron, and so that's the ground state. So let me rephrase that. The level, that's where the level where the energy is the lowest, that's called the ground state. So that's where usually atoms reside. Their electrons, they populate the ground state configuration. We'll talk about more about configurations in a sec. Okay, next is excited state. One or more electrons have absorbed. So when we say excited state, is that they have gained energy and can promote to another energy level, and that's where we absorb a photon of like a photon of light. Have absorbed energy. Have absorbed energy to raise them. To raise them to energy levels above the ground state. So that is where we can access the different energy levels from the ground state. And a ground state is usually n equals 1. There's no such thing as n equals 0. That would not make sense. That would not make sense. Okay, let's move on. So the thing about you think about energy states, they have energy, right? They're unstable. So think about things that have energy. You want to give off that energy. Like if you're feeling really excited or you're really amped to do something, like maybe during this, like maybe a soccer game or something, you have a lot of energy, so you want to use that to try and score a goal, right? So excited electrons, same thing, they're unstable, so so the electrons, as they're promoted to a different energy level, they tend to fall back down and give off energy as a result. So because they're just unstable that way. So excited electrons are stable. Are unstable. So what they tend to do is fall back to ground state. Ground state in one or more quantum jumps in one or more. So it can fall back, for example, 4 to 3 or 4 to 2 or 4 to 1, or do it incrementally to fall back to the ground state where it's the most stable, lowest energy state. And when we do that, we call it relaxation. Relaxation back to the ground state, photons of light are released. And the frequency is proportional to the energy difference between the two levels. All right, so the frequency is proportional to the energy difference between the two levels, like so. All right, so so say you fall from 4 to 1, the energy difference, the energy will be proportional to the frequency of light. So the energy released appears as a line spectrum. Line spectrum of the element. In the corresponding frequency or wavelength. So those lines will have, of course, will have a specific frequency and wavelength associated with its color. That's what it's talking about here. Okay, let's go back to what this quantum jump thing looks like. So let's go back to our lecture slide right here. Okay, can we see here that on the left here, I have my electron in the ground state n equals 1 level. And say now I absorbed a photon of light of this much energy. So don't worry about the slash mole. This is just an energy term for like a very large amount of energy. So say that electron absorbed a photon of light carrying this amount of energy, and now the electron gets excited and can access the n equals 2 level. So now we're at an excited state. Excited states are very short-lived because they're unstable. What we say like intermediate states. So they will quickly what we say like decay, or like the electron will fall back down to the ground state, and with it energy is conserved, right? So if it falls back down to the lowest energy level, then a photon of light must be emitted, and that's kind of the light we see in our everyday life. So when we're looking at like one of those line spectra, that line we see is because the electron has given off this photon of light here, and that's representative of the energy difference between the n equals 2 and the n1 level. So that's the largest energy gap between in the atom right here. So you have trouble visualizing this, I will come back to this picture. Is a very great example of how then the electrons, how they absorb light and what happens when they do, the energy associated with it. So when you absorb energy, you get promoted to a different energy level. And when you relax back down or fall down to the ground state, you go to release that same photon of light right here. Okay, so hopefully that gave people some concrete like visualization for that. I know it can be very, very abstract. So let's go back to the whiteboard. Well, I spent a lot of time talking, and we're only on like slide 18, I think. Yeah, and there's like 66 of them. So yeah, this chapter will take some time. So I don't expect it to finish it by this week. But that's good because this chapter is very heavy in abstract concepts. So I think we should take our time here. Okay, let's write in green this time. Okay, so now we're going to talk about contributions of Niels Bohr, which is the guy who came up with the Bohr model. We're also known for the Bohr radius of the atom, something you may encounter in physical chemistry if you guys are down that route. So, suggestions. Sorry, not suggestions. Suggested. A reasonable explanation for the atomic line spectra in terms of electron energies and he's the one who introduced the idea of quantized electron energy levels. So those specific energy levels that we were looking at. in the atoms. So the levels in modern dairy appear as what we call principal energy. And so that's like the principal energy level, and we can identify them, identify these energy levels with the following number. So they're identified by the principal quantum number. So there's a lot of quantum numbers we'll talk about. One of them is n. So quantum number. So whatever value of n, so like n equals 1 is talking about the first principal energy level, n equals 2, second, the 3 is third, 4 is fourth, etc. So we're now going to identify these energy levels as n equals a specific number. Okay. So now, so there's also other numbers, so we're going to talk about those. The atomic concept. That recognizes four quantum numbers. Four quantum numbers. By which electron energy levels may be described so there are four numbers that we should know. One is one is already what we talked about. So one is principal. So this is at the heart of quantum mechanics, or this atomic concept, that the electrons can be described by these four numbers, and it'll have specific values. So principal energy level, we have now called the sublevel. We'll talk about what that means later. The orbital, and then the number of electrons in said orbital. Electrons in an orbital. So that one we're talking about quantized, that amount limited to a discrete set of values. These are the values. Each electron will have a specific value for each. And then we'll learn about what values they can have and what values they cannot have. So we'll talk about more about this. So don't worry if this is kind of confusing right now. Okay, let's talk about principal energy levels. Principal energy levels. Okay, so they're identified by principal quantum number n, principal quantum number n. Let's not underline it, it might be confusing. So n is the principal quantum number. So mathematically, there's no n to the amount of principal quantum numbers, but so mathematically, There's no end. No end to the number of principal energy level of principal energy levels. But what we know based on the elements, the seventh level is the highest occupied by ground state. By ground state electrons in known elements. So the energies tend to increase as the principal quantum numbers increase as well. So for example, so the energies increase as the principal quantum number principal quantum number increases. So for example, n equals 1 is less than n equals 2, because that's the you see how in the last diagram where the quantum jump, you see that the energy level between n to 2 is the greatest, but then as we get to the n to 3 level, that energy tends to decrease, and as we go further up, the separation of the two levels as we go up, they tend to decrease. So and that has to do with the force of attraction between the nucleus as the radius increases outwards away from the atom. So n equals 1 is less than n equals 2, which is in turn less than, etc., eventually to n equals 7. Okay. Okay, so now we're going to talk about sublevels. So it would be nice if they had like circular orbits that were kind of all the same type, but that's not the case. Actually, atoms, they have something called sublevels. So there's energy levels, but within the energy levels is an inception type of thing. You have sublevels. But don't worry, there's no such thing as sublevels to our knowledge anyway, as of yet. So let's talk about sublevels. So the sublevels will kind of reconnect what sublevels are and how they are connected to what we see on the periodic table. That'll be something down the line. So levels into which principal energy levels I cannot write S's today, are divided. So they are specified as S, P, D, and F sublevels. So I will highlight this because that's something you should definitely I guess that doesn't work. My bad, guys. Oh, here we go. So you want to pay close attention to this these terms, so the S, P, D, and F sub levels. We also call them subshells. But I'm not sure if that term is used as often these days. So what does that mean? A specific sublevel is identified by both principal energy level and sublevel. So it'll have, say, maybe the 1 principal energy level and the sublevel will be S. So here's an example, actually. Example here. Example P sublevel. P sublevel in third principal energy level is 3P sublevel. Is the 3P sub. Let's see, we denoted a specific sublevel by the principal quantum number n equals 3, and P to denote the P sublevel. And then lastly here, number of sublevels. So the number of the sublevels within a principal energy level is equal to n. So for example, the n equals 1, there's only one sublevel, and that turns out to be S. We'll talk about the others as we go along. So is equal to n, or the principal quantum number. I'm surprised there's no exercises yet. This seems very, very text heavy. All right, here's an example of what I mean. Example here. N equals 4 has four sublevels. So it has 4 sublevels. Let's not use the colon here. So it has 4S, 4P, 4D, and 4F. So F, to our knowledge, is the highest sublevel. There is technically G, but we do not know any elements that have that extra sublevel. So F is the last sublevel that we'll have to know. Okay, let's check time here. All right, a little bit over 5 minutes. Okay, let's talk about the next thing for elements. For elements other than hydrogen, energy of each principal energy level spreads over a range related to the sublevels. For example, and n equal to So at n equal 2, the increasing order. Order is 2s is less than 2p. So as you go higher into the sublevels, the order is, as we listed them, S, P, and D. The energy decreases as we move from S to P to D. And that has to deal with the size of the orbital, what it looks like. Sorry, excuse me. And like how far away the orbital is from the nucleus. So at n equals 3, the increasing order is 3s is less than 3p, which is less than 3d. Then, as you may have guessed it, at n equals 4, we just add the f orbital. Order is 4s is less than 4p, which is less than 4d, which is less than 4f. Oops. Right. So other than hydrogen, because the hydrogen, it only has one sublevel, so that's S. So you can't really compare them. But as you go further away from the nucleus, and atoms with n equals 2, n equals 3, n equals 4 will have this order of energy for the sublevels. Okay, so let's see. So okay, let's look at how they're arranged here. Okay. So we should all see this. We can see our energy here from sublevels 3 to 4. So we see here S is the lowest in energy, and as we go up to the P, it increases dramatically. Then the 4S, 3D. Okay, so you may be asking yourself, why does the 4S come before the 3D, even though 4 is increasing in energy? So it turns out that in general, S orbitals are lower in energy than D and P orbitals. So in this case, the 4S will be lower than the 3D because the 4S, it has a different shape. So it'll be relatively closer to the nucleus, and that is just how the ordering goes. There is some other explanations for why the 4S appears before the 3D, and that has to do with how whether or not it's filled with electrons. But usually 4S, according to the periodic table, if you look at the periodic table, we'll talk about how these orbitals and the sublevels are connected. But the periodic table is actually arranged in the order of these sublevels. So it's a kind of a neat way to show how the ordering of the energy levels is filled. But what I would take away from is that the 4S, because if it's an S sublevel, and the S orbitals are lower in energy from that trend we just talked about, is lower in energy than the D orbitals. You should always kind of refer back to the periodic table. We'll talk about how to figure out where the 4S is on the periodic table, and the S, the P, and D orbitals. We'll talk about that. But usually S orbitals are lower in energy than, say, D and P orbitals. And it just turns out that the position of the 4S is lower in energy than, say, the 3D. So I do not expect you to know why it's like that, but it has to do with the type of sublevel and its distance from the nucleus. So 4S lower than the 3D. And then as we see here, the usual trend is the same, 4P, 4D, 4F. Okay, guys, and that is time. So so I wouldn't, so don't worry too much about this diagram right now. We'll talk about what it means and how we can relate it back to periodic table. But that is it for today. If there are any questions, let me know. Please try to digest this information quickly. Not quickly, but go through it slowly to make sure you kind of on the same page and are understanding on what I'm talking about, because this stuff can be very abstract. But all right, guys, that is it. Have a great rest of the day, rest of the week, and I'm praying that this week goes by somewhat smoothly. But with the election tomorrow, I think we have to just brace ourselves for what will happen, what just happens. But anyway, guys, take it easy, and see you on Thursday.